These videos are offered on a pay-what-you-like basis. You can pay for the use of the videos at my website. There's a link to my website in the annotation. The address is www.freelance-teacher.com/videos.htm. Or you can just use the link in the annotation. Thank you. So let's try this problem.
Okay. E to the x derivative equals root x. E is a constant. The derivative of any constant is going to be 0. So no, that's not true. Yeah, okay. E is a constant squared, so E. Okay, I would just keep it as is.
Done?
Yep.
Okay, good. So you had made a mistake and then you fixed it. That's good. Before we talk about, though, there is another little mistake that you made here. Your answer isn't quite right. So you were right about the e squared term, but we've made a mistake in dealing with the natural log x term. A small mistake. Yeah. What is this?
That would be nx to the n minus 1.
Good. This is what's called, this is what's called a power function. So this is what's called the power rule. It's what you've been calling the n minus 1 rule. We've talked about the idea that it's very important in math and calculus to distinguish between variables and constants. Is this a variable or a constant?
It's a constant.
Well, that's obvious because it's a number, right? But the tricky thing is letters can be either variables or constants. Obviously, numbers are always constants, but variables can be letters can be either variables or constants. So what does the x stand for here, a variable or a constant?
X is a variable.
And how about the n?
The n is also a variable.
If you think about the examples that we've done before for power functions, that's not correct. Because when we usually use this rule, we usually write it as, say, x to the 4th prime equals 4x cubed, right? We've actually been plugging in numbers for n here. So does x stand for a variable or a constant?
X is a variable and n is a constant.
Oh yeah, I misspoke. Maybe I misspoke a second ago. All right, I don't know. So anyway, n is a constant. That's right. N is a constant here. Okay, good. That shouldn't surprise us because remember, usually we use letters from the end of the alphabet for variables like x, y, and z, and w, and v, and earlier letters like n for constants. So when does the power rule apply? When does the power rule apply? Should the base be a variable or a constant?
Base should be a variable for power rule.
And how about the power?
The power is a constant.
That's right. Good.
Power rule.
How about this? Is this a variable or a constant?
It's a constant.
How about this? Is this a variable or a constant?
It's a constant.
We've talked about that number e before. How about this? Is this a variable or a constant?
It's a constant.
So would we apply the power rule to this?
We would not.
No, because it only applies when the base is a variable. How do you know this is a constant? Well, the base is a constant and the exponent is a constant, so the whole thing is a constant. Is this a variable or a constant?
It's a constant.
Yeah. If you plugged in on your calculator e cubed plus root pi and then took the square root, you just get a single number. So this is a constant too. So these are all constants. So what's the derivative of this with respect to x?
0.
That's right. What's the derivative of this with respect to x?
0.
What's the derivative of this with respect to u?
0.
What's the derivative of this with respect to z?
0.
It doesn't matter what variable we're taking the derivative with respect to. The derivative of a constant is always 0. You don't use any other fancy rules for those. Okay, good.
Okay.
So, does this look like it stands for a variable or a constant?
It's an R, correct?
That's a K, actually. That's my cursive K.
Okay. Well, K would be a constant, most likely.
It's from earlier in the alphabet, and it also, K stands for constant in German.
Okay.
So what's the derivative here?
0.
That's what we could call the constant rule for derivatives. So on the problem we were just working on, this problem was trying to trick you into applying the power rule here, when what you really should be applying is the constant rule. At first you fell for the trick, but fortunately you had second thoughts and you caught yourself and you fixed that. So you came up with the correct answer. This was one of the problems from the sample tests, so it's important, your instructor wants you to understand how to not fall into that trap. Okay, now, so here we had our power rule. Let me write down this then. Here's another function. Does it look like the base is a variable or a constant here?
It's a constant.
How can you tell? Well, it's a letter from the start of the alphabet. And does it look like the exponent is a variable or a constant?
The exponent is a variable.
You can tell because we're using a letter from the end of the alphabet. So, would you agree this is not a power function?
Yep.
Because a power function has to have a variable raised to a constant. But this is a constant raised to a variable. A totally different thing. Okay, so this is a whole other thing. This is not called a power function, so we need a new name for it. This is what's called an exponential function. What's the difference between a power function and an exponential function? Obviously, the names make sense because they have powers and exponents. But the convention is power function means the base is a variable and the exponent is a constant. But exponential function means the base is a constant and the variable and the power is a variable. Oftentimes students don't distinguish clearly enough between those. So here we have a exponential function. Good. Here's an example that we've already talked about. We've already talked about this function. Is this a power function or an exponential function?
That is an exponential function.
How can you tell?
Because e is a constant and x is a variable.
Right.
The base is a constant and the exponent is a variable.
So this is a type of exponential function. The specific name for this is called the natural exponential function. This is by far the most important exponential function. So sometimes when people say exponential function, they just mean this. But technically, anything like this is exponential, and this is the natural exponential function. Okay, good. So how would we find this derivative? Would we apply the power rule here?
We would not.
No, because it's not a power function. It's an exponential function. What is this derivative?
0. It's just itself. It's e to the x.
Right, yes. Is this function a constant?
It is.
Let's be a little careful with our terminology here. Is the entire function a constant?
It is not.
No, because the exponent is a variable. It has a constant in it, but it's not a constant. You can check that on your calculator. Is e to the 0 the same as e to the 1? No. And is that the same as e to the 2? No. And is that the same as e to the 3? No. So changing x definitely changes the function here. Okay, so this is not a constant. You're only a constant function if everything in the function is a constant. So this is just a special derivative that we'd already learned, you and I together. We'd already learned e to the x. So what do we have left to do? Well, what we need to do now is we need to figure out what the derivative of a general exponential function is. So first of all, could we apply the power rule here?
We cannot.
No? How do you know you can't?
Because a is a constant and x is a variable.
Which is the opposite of what it's supposed to be for a power function. Good.
Mm-hmm.
So could you say that the derivative here is just x to the a to the x minus 1?
Nope.
No, because I just did what we said we were not going to do. That would be applying the power rule. You're not allowed to do that. So what do? Well, you just have to memorize what the derivative of these functions are. It's just a brand new rule to memorize. Have you had a chance to memorize that yet? Do you know what the derivative is here?
A to the x. Well, it's the same as above, right?
So you're saying this would be the derivative?
Correct.
Okay, that would be nice, but it turns out that this simple type of derivative only works for the natural exponential function.
Okay.
It doesn't work for other bases. So I'll tell you what it is, or maybe you can look it up on you have your cheat sheet with you?
Mm-hmm.
So let's look at that and see what do they tell us.
E to the, well, a to the x. Okay.
So what should I write down here as the derivative of ax prime?
We should write the natural log of a times a to the x.
Okay, good. So notice this simple derivative only works for the natural exponential function. It doesn't work for more general exponential functions. So we just need to memorize that this is the correct way to take the derivative. Okay, good. All right, so stare at that. Tell me when you think you got that memorized.
Natural log of a and then a to the x. Okay.
Okay, well, let's try this problem then.
F of x. So this is really a to the x. So 5 times 5 to the x. Okay.
Okay. If we have it memorized, it's not really that hard to apply that formula. Very good. Let's check that answer on our calculator.
Natural log of 5 times 5 to the... Okay. Well... And then I could set this my math function. Derivative of 5 to the x comma, x, comma, 3, close parentheses. And then I get the same number.
Okay, excellent, good. So again, it would be good, we're not going to usually check on the calculator, but it would be good to, on your own, to practice checking these on your calculator. Very good, so that's our answer. All right, I'll go back to my screen.
So I was going to use that on the quiz today, and then I realized as I was going to turn it in that the backside was incomplete. So, yeah.
You mean you were going to use checking on your calculator?
Yep.
Yeah, okay. Yeah, so my advice would be basically it can be time consuming to use your calculator. So the best thing is like you figured out, first just make sure you've done all the problems. And then use the time you have remaining to check things on your calculator. Although, you have to use your own judgment. If you have time left over, is your time going to be better spent checking things on your calculator or just double checking your algebra? You have to decide which is going to be the best use of your time. I know it can be time consuming to type things into the calculator. And the problem is, if the calculator gives you a different answer than you figured out on paper, you don't know if that's because you made a mistake on paper or maybe you made a mistake entering it on your calculator. So I know that can be frustrating. So obviously your goal on the test is to get the best score possible. So on the problems where you think it's helpful to you to use your calculator, go ahead and do that. But sometimes you might feel it's a better use of your time just to check things on paper. I do think it's a good use of your independent study time to keep checking things on your calculator so that you're improving your calculator skills so that you really can use that during the test with some confidence. But obviously during the actual test, you just want to use your time, whatever you think is the best use of it to get the best score. Okay, so let's see here. I was going to write down, oh, yeah, so... Okay, let's try this one.
Okay. Okay. Well. So, so I guess based on our rules so far, this would be correct, but I'm not sure if you can follow that rule with when x is so could it just be 2u times u? Oh yeah. Okay, I'm just going to go with this.
Okay, so going back to our rules, you're trying to use the rule for the derivative of a exponential function. Now, I guess I was a little sloppy here because I didn't quite emphasize something that's important about this rule. So when we talk about the power rule here, so here's the power rule. So what's this derivative?
4x cubed.
So what's this derivative? Is it 4 times x squared plus 2x cubed?
It's not. We have to use chain rule.
That's right. So remember that all of our simple rules for finding derivatives only work when the input to the function is just a single variable all by itself. Every single simple rule that we've learned for finding derivatives only works when the input to the function is just a single variable by itself. If the input to the function is itself a function of a variable, then you can't use that simple rule. So this would be wrong. We're not allowed to do that. All right, so I forgot to emphasize that that rule that's been true for all the simple rules we've seen is also true for, well, let me ask you this. I guess we should have been able to figure it out because what's this?
That's e to the x.
So does that mean that this derivative is this?
It does not.
No, because that rule for that natural exponential function only works when the input is just x all by itself. When it's a function of x, you can't use that simple rule. So you were struggling with this. I could tell that you were uncertain here. Well, here's how you could have settled your uncertainty. If you had remembered that our rule for the natural exponential function only works when we're inputting a single variable, that could have reassured us that the same is true for these in general. So all of these simple rules, including this rule for exponential functions, this only works when x is just the single variable. So would this rule work to find this? Could we use this simple rule here?
A to the z. Yep.
Yeah, because we're just putting in a single variable. Would it work here?
Mm-hmm.
Would it work here?
One second. It would.
I think you might be misunderstanding what I'm saying. So by a single variable, I mean things like this. Anything more than that, this is not a single variable. It's a constant times a variable. Or this is not a single variable. It's a variable squared. Or this is not a single variable. So it's a little hard to put this into words, but by single variable, I just mean just that one letter all by itself.
Okay.
That's the only time that these rules apply. So could we apply this simple derivative rule to this function?
We cannot.
No, we can't, because we're not just plugging in the single variable w, we're plugging in 3w. Okay, I think you were starting to suspect that might be the case here, but then you gave up on that and went back to your first idea. So let's go back to that problem and try again. So if this simple rule does not apply, how are we going to get around that? So let's go back and see if you can figure out any way to solve the problem if we can't just apply the simple rule directly.
Okay. Okay, so chain rule 2u inside function. Derivative of 2u, we're going to use the constant to a variable. So natural log of the base. Okay.
Okay, good. All right. Now, you'd already when you were doing this problem before on your own, you'd already kind of taken a stab at doing it this way using the chain rule, but you were just a little bit half-hearted about it and you gave up on it in the middle. But this time you carried it through and you did it correctly, and we got the right answer. So the original function here was 2 to the x squared plus 4x. Can we apply our simple rule for finding the derivative of an exponential function to that function?
We cannot.
No, because the exponent is not just an x. It's an x squared plus 4x. How did the chain rule help us? Do you see how the chain rule helped us? Because it took one complicated function and turned it into two simpler functions. That's our basic strategy here. Anytime we have a function that is too complicated for us to take the derivative of, our strategy is to try to rewrite it as simpler functions. So notice then you have a line f prime of x equals 2u prime plus x squared plus 4x prime, your third line. Notice how that took the original function and split it up into two simpler functions. Do we know how to take the derivative of both of those? So can we use our simple rule for the derivative of an exponential function? Can we apply that to the derivative of 2 to the u?
Yep.
Yeah. Do you see how that's an advantage? Because before the exponent was complicated, x squared plus 4x. And now we've simplified it to just a single variable. Remember that the rule only works if the exponent is just a single variable all by itself with nothing else at all there. Well, that's what the chain rule allowed us to do. So eventually we were able to use the rule for exponential functions after we used the chain rule to simplify. Okay, so what's the biggest mistake people make oftentimes in calculus? One of the biggest mistakes I mentioned earlier today is not using the chain rule when they need to. One of the most common mistakes people make is not using the chain rule when they need to, trying to apply the simple rules when the function is too complicated to do that. And that was what went wrong the first time we tried that. But now we have that right. Okay, so I'll go back to my screen. Let's try this problem.
Okay, so we can't use that. It's 3, yeah. Okay, so 3u, natural log of 3 times 3u, derivative of 4x cubed minus 2x. Okay.
Good. What would be the most common wrong answer here? Well, a lot of people might say the answer is f prime of x is natural log 3 times 3 to the x to the 4th minus x squared, and then just end it right there. they don't realize that there's also an inside function that they have to take the derivative of. That's the mistake we saw in the previous example. But now we got that correct. Okay, good. Let's actually scroll back up to the previous example. Good. If you take another look at that, you can see we didn't actually quite finish that problem. So let's go ahead and finish it.
Okay, so we plug in 0, so 2 to the 0 is 1. Natural log of 2 times 4. Okay.
Good. Okay, good. That's right. Okay, let's try this one.
Okay. So it's not a single variable, so for the sine x for u, sine x, sine of x, log of natural log of 4 times derivative. Okay.
Okay, that's good. All right, so again, a common mistake might be to say that the answer was natural log 4 times 4 to the sine x and just stop right there. The most common mistake is not realizing that there's an inside function and that we have to take the derivative of that as well. So that was the correct approach for that problem. Good. I'll write down another problem. Let's try this one.
This one. Log of u is natural log of 3 times 3 to the natural log of 1. Oh. And I guess I could check this. This would be a good one to check with. So go ahead and do that math. Let me scroll up. Okay. Derivative of 3 to the parentheses natural log. Yeah. The natural log of x plus 1 comma x comma 0. Okay, yep, I'm gonna get the same answer.
Okay, good. All right, this is a harder problem than we've done so far, but you adapted to it and figured it out. What was the justification for your third line? What were you using there?
This is chain rule.
That's right. And then what was the justification for your fourth line?
We went from chain rule again.
Yeah. When we're doing a more complicated problem like this, it's good to write down those two justifications. Good. So in previous sessions, we've done this for other types of functions. Sometimes you have to use the chain rule twice in a row. So it's good that you adapted and saw that here. In this case, not only do we have a function inside of a function, it's more complicated than that. We actually have a function inside of another function inside of another function. The x plus 1 is inside of the natural log, and then the natural log is inside of the 3 to the power function. So you have to carefully split those apart. Good. Now, in your third line, you wrote down 3 to the u. What does that u stand for?
The u stands for the u stands for the inside function.
And what is the inside function?
The inside function is the natural log of x plus 1.
That's right. You simply took the original function and you replaced natural log of x plus 1 with u. Good. Then in your fourth line, you have a u on the right-hand side, natural log of u prime. Take a look at, point to the u on the right-hand side. What does that u stand for?
This is the inside function on this side, x plus 1.
It doesn't stand for the same thing as the previous u, does it?
Right, so let's use a different variable.
Yeah, it's poor notation to use the same variable to stand for two different things. Remember that every time we use the chain rule, we have to make up a new variable. Well, if you choose the chain rule twice, you got to make up two new variables. Let's use v. There's nothing wrong with p, but v is closer to u. Okay, good. All right, that is an important notational thing to make our work actually clear. If you use the chain rule twice, you want to use two different made-up variables. But other than that, it's good that you saw that this was a case where we had to apply the chain rule twice. That's a pretty hard problem, but there was a problem like that on the sample test, so it looks like you could see that on the real exam too. So you took your time and avoided mistakes. That was a good process there. All right, I'll write down another problem.
Okay.
Okay, let's try this one.
Okay, so I'm going to use okay. Okay, so we started with this, we used the quotient rule, and we used, well, we just found their derivative, and then 2x, sin of x, prime of x times 2x. Log of 2 times 2, log of 2 times 2x. Okay.
Good. Okay. So here was an example of using the exponential function together with the quotient rule. It looks like we avoided mistakes there. That's good. That was a good process. Let's try this one.
So this is not a single variable. So I'm going to second e to the 5. Okay, so, oops. My answer is negative 0.101. I'm going to double check that. Derivative of second e, e to the...
Let's back up there for a second. So let's go to my screen, and I'm going to type what you typed onto my calculator. So, whoops, one moment. Okay, so you did e?
Yep.
Then what did you type?
E raised to the... I didn't put parentheses, I put a...
So maybe you used this e key.
Yeah.
Then
okay,
you raised
yeah.
it, and then what?
E raised to the negative 5 times 3 times negative 5.
Okay, can you see any problems with this? So the problem is, how is the calculator supposed to know that these are both in the exponent?
Okay.
Right? Here's what the calculator thinks that you're doing. The calculator thinks, if you type it in like this, the calculator thinks you're doing this. Right? So how can we tell the calculator that both of these numbers are supposed to be in the exponent?
Use parentheses.
Right. This is a case where it might be better to use this form of the E key, because that puts the parenthesis in for you.
Okay.
You can use the other E key if you want, but then you have to put the parenthesis in if there's more than one thing in the exponent. Yep, this is the downside of using the calculator. Sometimes if you get if the calculator doesn't give you the same answer, it's hard to tell whether that's because you made a mistake on paper or because you made a calculator mistake. But that's why it's good to keep practicing. If you practice this enough, you'll build up your calculator skills to the point where you can use it with more confidence. So let's try again to do that since we started on that.
Okay. So I have e to the negative 5 times 3. Okay, that should be correct. Let's see. 1. Okay, let's see. Derivative of e to the negative 5x parentheses, comma, x comma 3. Yep, I get the same answer.
Okay, good. You can see that the problem here is at first you were not going to get the same answer, but that didn't mean you made a mistake on paper. It was a calculator problem. But it's good that you're practicing that. If we practice that enough, we'll be able to rely more on the calculator to check our work. Okay, so the main thing I wanted to do here was to review that this is the natural exponential function. I guess I'll go back to my screen now. So notice that you shifted to a different derivative formula. Let's see, where's my... For general exponential functions, you would use this formula for the derivative. But here you shifted back to the simpler formula because this was the natural exponential function. It actually turns out that you could actually use this formula even for e to the x. This actually will give you the same exact answer if you use e to the x. It's not, maybe that might not be obvious, but it's certainly simpler to use this simpler version. That's what your instructor will expect. So the way you did it was the best way. Okay, good. Let's see. Okay, let's try this one.
Okay. Okay, so 3x squared plus okay.
Okay, good. This should be pretty easy. I just wanted to give you an example that had both a power function and an exponential function in the same problem so we can compare them. So the mistake people make is treating these as if they're the same thing. They kind of look similar because they both have a base and an exponent. But what's the really big difference? Why is x cubed treated totally different than 3 to the x?
Because x is a variable. Well,
Right.
sorry. Yeah.
So one of them has the variable in the base, and the other one has the variable in the exponent. That might seem like a small difference, but it turns out to be a huge difference. So we don't want to confuse those two different types of functions. They look similar, but they mean totally different things, and they're handled totally differently. Okay, and you did that correctly. I'll go back to my screen. Okay, so I think we made some good progress on those exponential functions. So let's move on to another type of function that looks like it will be on the test. Okay, so let's copy this question down carefully. What's the answer here? How would you solve this problem?
We could use our calculator to find the natural log of 5. And that comes out to be 1.61.
Okay, very good. So that was a trap. I was trying to trick you into taking the derivative. But you paid attention to what I wrote down. I didn't ask you for f prime, I asked you for f. So you just used the original function. So we just had a little review here on how to find natural logs on your calculator. So you did that correctly. Do you remember how this is read? How do we read this aloud? What do the symbols stand for in words?
It's a natural log. Sorry, the natural log of x.
That's right. This stands for natural log of x. That's what we've already covered. Now we have to cover a new type of function, this type of function. Do you know how this is read aloud? This is read log base 2 of x.
Okay.
Log base 2 of x. So how would this be read?
That is log base 5 of x.
That's right. How is this read?
That is log base 7 of x.
Good. How is this read?
Log base 10 of x.
Now, a lot of the time in math, logs are written without the base because you're supposed to know what the default base is. Do you know, if we don't write the base, what do we assume the base is?
10.
That's right. By the way, notice this is not the natural log. Natural log is something totally different. That's actually a log base e. So ln is not the same as log. So this is the log base 10. All right. If you look at your calculator, do you see the log button, log?
Yep.
All right. When would you use that? That's used to find the log base what?
Base 10.
Yeah, that's only used for finding log base 10. If you look, you'll see there is no button for log base 2 or log base 7. So we need to learn how to do this. So, for example, how would we do this? So first of all, is this asking us for the derivative?
It's not. It's
No.
a function.
So we just need to know how to do this on the calculator. Do you know how to do that? I can show you. So it's actually not obvious. So we have to go to one of our menus. So you go back to our trusty math menu. And maybe you can find it on this list. Yeah, there we go. All right, so would you agree that A looks like a good candidate? There we go. So this is how you find, this is what you use for logarithms besides the natural log and log base 10. Do you have that on your calculator?
It doesn't seem like it. Let's see. I have 8, 9, and then nothing. 0 is solver, and there's nothing after that. There's no A or B prompt. Let's see. Maybe in a different...
Can you scroll down below them? Or does that just scroll you back to the beginning?
It just scrolls me back to the beginning.
Ah, that's lame. Okay,
Yeah.
I guess you have an older version of the software. All right, I'll have to give you another way to do this then. All right, so the other way to do it is this. You'll have to, it might be under a different menu, but I don't know where to find it on your calculator. So here's the other approach. So on my calculator, we would do, then that would be log, and we need to go over this because you might have to do that plugging in to find specific logs on the test. So this would be log 5 divided by, so it's the log of the x divided by the log of the base.
Okay.
So what do you get when you do that?
Log 5 divided by log 2. 2.32.
Okay, that's right. So since we can't find the option to do that directly on your calculator, that's the formula for doing it. Or that's a formula for doing it. There's a couple different ways to do it. Okay, you could also do this with natural log. All right, so see if you can adapt to this one then. How would you find f of 4 here?
Okay, so f of 4 would be the log base 4 over log base 2. Oh, sorry, log base 4 over log base 3. And then that comes out to be 1.26.
Okay, yeah, you did that correctly. You didn't quite describe it correctly, but you did it correctly. So I think you read this as log base 4 over log base 3, but these are not the bases. This little number down here is a base. These are not the bases. These are both log base 10s. So you would just read this as log of 4 divided by log of 3.
Okay.
But in any case, you did it correctly. And what did you get?
1.26.
Okay. Okay, so that's our expedient for figuring out those types of logs on your calculator. Okay, now let's say we were trying to find f prime of x. We have to memorize another derivative formula for that. You might not have memorized that yet. See if you can find it on your cheat sheet.
Okay. Okay, cool. 1 over the natural log of a times x. 1 over the natural log of a times x. Okay.
I think I'm going to write that like this. Because if you write it this way, you don't need as many parentheses. But would you agree this is the same as on your handout?
Mm-hmm.
It just, we don't have to put in quite as many parentheses to clutter up our work. Okay, so what do you think this derivative would be?
This derivative would be 1 over x times the natural log of 2.
Okay, good. So notice, what number do we take the natural log of? The base.
Okay.
And then this is the input to the function. Now, when does this work? Does this stand for a variable or a constant?
It's a constant.
And what does this stand for, a variable or a constant?
X is a variable.
And just like all the other simple rules that we've learned, this simple rule only works if you're taking the log of just one single variable all by itself. So it would work to find the log of x, or the log of y, or the log of w, or the log of z, but it wouldn't work if you were trying to find the log of 2x, or the log of x squared, or the log of x plus 2x. It only works if the input is just one single variable all by itself. If it's anything more complicated, we'll have to use some other trick to simplify. Okay, good. All right, so stare at this. Tell me when you think you have that memorized.
Okay.
All right, well, I will scroll it off the screen because we've got it memorized. And then I'll write down a new function, and then you can tell me what the answer, work out the answer on your screen.
Okay. So f of x equals the same problem. Okay.
Okay, excellent, very good. How would you read the original function aloud?
F of x equals the log base 7 of x.
Excellent, and how would you read your derivative aloud?
1 over x times the natural log of 7.
That's right, very good. Okay, that's the correct way to apply the formula. I'll go back to my screen. Let's try this problem.
Okay. Okay, so function. Okay.
Okay, that's good work. So now we integrated what we just learned about the logarithm. We integrated that with the product rule, and you did that correctly. That's good. I'll write down something else. Let's try this one.
log of 3x plus log base 3 of x plus the natural log of 3x. So when you chain rule for natural log of 3x, chain rule of natural log of u, right, derivative of natural log of u is 1 over u times the derivative of 3x is 3. Plug the inner function back in for u. That's correct. 1 over x times natural log of 3. Okay, this should be good.
Okay, good. That was a good process. That was a little harder problem, but you took your time and got it right. So you saw that you needed the chain rule at one point. That was a good approach. Okay, good. That was a good, careful process. I'll go back to my screen. Notice, how do you read this aloud, this term?
That is the log base 3 of x.
And how do you read this term?
That's a natural log of 3x.
Notice that you used two different rules to find those two derivatives, right? For the first term, you used this rule. But for the second term, you used the chain rule, and then you used the rule we already learned for derivatives of natural logs, which is this rule. All right, good. So we have two different rules for these two different types of logs. It turns out that actually this rule also works for natural logs if you understand how to apply it. But for solving problems, it's simpler to treat them as two separate cases. So you did this correctly. For solving problems, we use one rule for this type of log, and then we use a different special rule for the natural log. So the way you did that was good. That was a good approach. Okay. We don't want to confuse the natural log with the other types of logs. We have two different approaches for those. Even though technically they are very similar, we're not really treating them similarly. Let's try this problem.
Okay. So inner function. Huh. 1 second. 2 cubed is 8 plus 5 is 13 times natural log of 3 times 2 squared is 4 times 3 is 12. Okay.
Done?
Mm-hmm.
Okay, good.
Well, I guess I should solve for a number.
Let's go ahead and do that.
One divided by 13 times. Okay.
Okay, looks like you were careful and put in the parentheses that you needed there. So 12 divided by 13. Okay, good. I suspect your instructor might give you full credit if you just wrote it as 12 over 13 natural log 3. That gives you an exact answer rather than approximate, but I think it's good practice to know how to do it on your calculator to get the decimal answer too. All right, so what's the most common mistake people would make on this problem? Well, one of the most common mistakes is to say that f prime of x is 1 over x cubed plus 5 times natural log of 3, and then just end it right there. That is, a lot of people would just try to take the derivative of the log without remembering to take the derivative of the inside function. They might not even realize there is an inside function. We've talked about that mistake before. Remember that we can only use our simple derivative rules when the input to the function is just one single variable all by itself. Anytime there's anything any more complicated than one single variable all by itself as the input, basically we have to use the chain rule, which is what you figured out here. So this is the first time we had to use the chain rule for these types of logarithm problems, but you figured out on your own that that was what we had to do here. So that's good. Okay, so that's a good approach to working that out. We've also seen how to actually figure out the logarithms on your calculator. But actually, it looks like you might not actually, with that formula we talked about, it looks like you might not actually need that, though, during the test, because the logarithm itself seems like it usually disappears in the derivative. And the derivative just involves the natural log. But just in case, we went over how to find those on the calculator if you need those. These videos are offered on a pay-what-you-like basis. You can pay for the use of the videos at my website. There's a link to my website in the annotation. The address is www.freelance-teacher.com/videos.htm. Or you can just use the link in the annotation. Thank you.